everyone. I'll quickly walk you through the agenda of today. So we'll explore a bit what concept drift is in general from a theoretical standpoint and what different forms of drift can happen and be present in your time series. Then we go on to stock market forecasting and how concept drift affects the forecasting and how we assemble the data set, which we now the AZP data set, to actually carry out simulations with the real data and test our solution. Then Giacomo will guide you through what an ideal transaction is, or the concept of ideal transaction, and we will explain our adversarial training and validation setup. So let's start from concept drift. The term concept drift denotes the dynamic evolution of data over time, and it is present in diverse domains beyond finance, specifically like weather prediction or language processing. And back to finance, like being able to understand its underpinnings, it's crucial for the role in the forecasting and being able to provide like a robust forecasting in the market. As you can see here, a quick formula. The problem that we're trying to correct and be robust on is we have a probability of X given Y that changes over time. Like after some time delta, below and the bottom, the two probabilities have changed even though the concepts are the same. And here on the right, we can see an example from like a fun example with the word cool in the 80s had a meaning, in the 2000s started to have a different meaning. The concept was the same, but some time had passed, and we have to be able to model the difference in the concept as well. So what are the most common forms of concept drift that we are aware of? We have virtual concept drift and real concept drift, which we'll see in a second. So what is virtual concept drift? It's a drift that occurs when the data distribution changes over time, and it is an apparent shift in distribution which actually does not change the true outputs. It can be observed in scenarios where there is noise or external factors that influence distribution, while the underlying truth remains constant. So if we go back to the formula, we can see that after some time, we still have the same Y, so YS is equal to YT, but X has changed due to some noise or external factors, eta. On the right, we have real concept drift, which is instead defined as a drift that involves changes in the true outputs over time. So it is an observable shift where we have differences in the in-distribution instances. So for instance, consumer preferences, economic recessions, technological advancements. So as you can see here, X is the same, but the truth has changed. So YS is different from YT. And this one on the right-hand side is what we will focus on for today. So the virtual concept drift will be passed on. So in the realm of real concept drift, what are the different forms that we can find or encounter? So we start from sudden concept drift, incremental concept drift, gradual concept drift, and finally recurrent or cycling concept drift. So as you can see here from these figures, it's quite easy at the conceptual level to understand what they're all about, but we will go through one of them one by one in more detail. So let's start from sudden concept drift. So it is an abrupt shift in distribution at some specific time step. So here we have the time axis vertically placed. So at some specific time step, we have an abrupt shift. And so it can occur at a given time step where we suddenly change the previous distribution into a different distribution. And it unveils some drastic changes in the distribution, which is also quite unexpected. And we have an historical example, the 2008 financial crisis, which is very on the point as like a declarative example of a moment where we had seemingly stable market conditions which abruptly shifted. Of course, this means that we need to build models that are able to swiftly adapt to unforeseen circumstances on the fly and can learn them like very easily and quickly. So like we expect models that when they are roughly at this mark are able to understand that we are on a different distribution, not on the prior one. So indeed, we need to enforce real-time responsiveness in the models. Then we have incremental concept drift. This is a steady transition to a persistent new distribution, which means that we don't have an impulsive transition from state A to state B, but it will take some time. It is a slow and gradual shift that persists though over time. So after some time, we will find ourselves in a completely new distribution. Here we can find examples indeed in economic recessions or the slow evolution of societal attitudes towards technology. Of course, this is not related to finance, but this is quite an illustrative example. So for instance, when some brand new breaking technology comes out, it will take some time for people to adapt, but when they do, they will actually shift their attitude in a completely new distribution. So of course, this needs the model to adapt to subtle shifts in times, because they are not abrupt, they're subtle if you look at like subsequent shifts, but the model needs to be able to navigate through these dynamics in order to have a robust model. Then we move on to gradual concept drift. This is similar to the previous one, but the transition is oscillating between the previous state and the next state. So it is a combination of sudden and incremental. So this involves an unstable transition that captures high frequency dynamics of market evolution over time. And of course, this goes to like period of gradual drift in global markets. Of course, global markets are such large entities that it will take some time to actually establish their new distribution. And for this reason, we will have an oscillating distribution during that like assessment time. It is also akin to businesses adapting to changing environmental norms, because it will go back and forth towards the new state and the previous state. So yeah, this is quite an important drift because it happens quite a lot in real data, as we will see in a few minutes. We'll close with cyclic concept drift. This is the easier one to grasp, but as you can see, the idea is that we have a repeating transition, the distribution that will take us to a new distribution back to the starting one with some periodic recurrence. Of course, this is akin to the cycles of technology stocks in various industries, and it requires models to learn and capture the extent of the cyclic pattern. So how long is this length right here? So how long is this period before we actually re-trigger a new sequence? And this is maybe the easier one and most known one, because it's also akin to seasonality and trend, which are two very common terms in time series forecasting. So let's move to stock market forecasting and indeed how concept drift can affect that. So we'll introduce a concept of buy and sell points, which you can see in this figure on the right. So of course, the perfect and ideal situation is one in which we buy where the price is at the lowest and sell when it is at its maximum. But of course, understanding and isolating when these moments happen is quite difficult, because the market is volatile and because concept drift can alter its representation and the decision making that investors have. So the concept drift that we're modeling with the real-time learning and adaptation, it's crucial and at the core of constructing a model, an investing model that is actually sustainable and profitable for the investors. Otherwise, we will have like detrimental consequences like we had with the Black Monday in 1987 and flash crash in 2000, where the conditions were not static and the evolution was too abrupt to be grasped. So yeah, the intrinsic volatility of stock market has direct consequence on investor behavior. So having a model which is robust to concept drift is important to let investors make the most informed decisions. So now we will talk a bit about the Italian stock market, which is the one where we focused on, because in our opinion, it is a perfect playground for stock market simulation. Indeed, it was deliberately chosen for its simplicity because compared to larger ones like the US or China, because it offers an advantage in addressing the challenge of like compelling data sets for concept drift. And while larger markets may have greater complexities that we were not able to highlight and study, the choice of the Italian market as research playground enables a more effective exploration of fundamental principles, understanding if our solution wasn't on the right track. So its straightforward nature allows the incorporation of more realistic assumptions in the modeling of the problem, which we used a lot and emphasized a lot in our simulation environment, where we actually replayed the data as it went along during the forecasting window. And the insights that we have drawn from our simulation experiments are still general enough that they can be applied. So I'll close with a quote from Paul Gillen. When you say ROE, do you mean return on investment or risk of inaction? Meaning that, of course, the volatility of the market may stall people, investors, make them stay still and prefer not to invest for the risk of losing money. But the risk of inaction is the actual greater ROE here, because it is even worse than not focusing on modeling a correct return on investment and addressing the problem of concept drift in such a volatile environment. So I will leave it now to Giacomo, that will guide you through the second part of the presentation.
Yeah, thank you so much, Federico. So now I will share my screen. Okay. Can you see my screen now?
Yeah, we can.
Yes.
Okay, perfect. So let's go inside the practical part, so how to tackle the concept drift problem here. So let's go for the basic concept here. So what we intend for related to a transaction, which is a transaction. So basically here, the kind of operation that we can perform, the buy operation and sell operation. That's an example of simple buy operation. You simply specify the type, that is a buy. You specify the price ladder, so the price that you use in order to take the buy. You specify the quantity that you want to buy on. So for the simple example, that's the net amount that you consider for your investment. But you have also to take into account that for each transaction that you make, you have some cost related for the platform that you use or the trader that you use in order to make this kind of operation. And you have to take into account fixed cost and also variable cost for this kind of transaction. And your total amount will be affected by the invested amount, the fixed cost, and the variable cost when you buy the stock. But the same thing happens also when you sell. So when you sell, obviously you have to choose a price higher, same quantity, and your net amount will be also affected by another fixed cost and also another variable cost. That would be your total amount that you have to consider minus this kind of cost. So basically, these are the two basic operations that we will use later. Next, what we mentioned is the P dataset. So it's the dataset that we use in order to test the adversary, in order to tackle the concept drift. Basically, this is a dataset recorded that records data over the past 3 years. Roughly, there are 400 stocks that are traded on the Italian market. And basically, this dataset will show you a little snippet here. The main fields here attribute will be the date time, the ticker, that is the code that identifies that specific stock, the ladder price and the ladder quantity, the money price and the money quantity. And if you ever trade in this field, you know that when you buy, you have to consider the ladder. When you sell, you have to consider the money. And as you see here is a screenshot for some date time, so only a few minutes related to only one stock. So imagine this kind of data set over the years, over different stock, over different days and months and year. So that's the basic data that we use in there. So let's start. Let's start from what we consider an ideal transaction or best transaction. As you see here, maybe a little bit smaller, but what we have here is a representation of a wallet. On the top part here, you have the total amount that you have inside your wallet, your cost of transaction. So this is the amount of cost that you have collected during each operation that you performed in the past, and the gain that you get on your single wallet here. On the bottom of the wallet here, you have the list of all the orders that you executed during the period. You see that you have always a buy and a sell operation, a buy and a sell operation. And if you see here, you see only perfect transaction. So you will see always the buy amount that will be higher than the sell amount. This is because this wallet was computed by looking forward in time. So in order to compute this kind of wallet, we looking forward, we choose for the best action to choose, and then only at that time we choose the best transaction to perform. So that we call the best transaction. Obviously, this is computed offline. So once we have computed the best transaction, we have to take into account some constraints when you have to evaluate and compute this kind of stuff. You have to consider like a forecasting window, so how much far you want to go in time. And obviously offline you have no such limitation, but when you will use this kind of approach in real time, the more higher will be the forecasting window, and maybe the less will be the precision of your prediction. So that's the trade-off you choose. Another important thing also when you go live is that you have to put like a limit to your wallet in case of a high amount of loss. So you have to limit the amount that you have to invest for that stock for security reason in order to suspend the trading. And another important stuff is this one. When you compute the best transaction for your wallet, you have also to choose the single amount that you want to use for your transaction. This is very important because maybe each stock has a different capitalization, and in that time you cannot invest, for example, 3,000 euros because there are no so much stocks to buy. So maybe some stocks allow you to buy that kind of amount and other stocks not. So you have to balance this value based on the stock that you want to trade. So after that, when you compute this best transaction, let's represent them. So a best transaction, we define that using the concept of exchange. For us, an exchange is the point in time where you start observing the stock, plus the point in time where you perform the buy operation, as highlighted here. So you buy with that amount, with that number of stock, with that price, and also the point in time when you sell the stock. So this range in time represents the exchange that you perform. So basically composed by a buy transaction, the sell transaction. So basically what you get is something like this. So inside an exchange, you collect all the observation from the point you start observing this transaction, where you compute the buy and when you compute the sell. In this range, we record the best transaction. And that's it. So that's an exchange. From this exchange, we compute what we call like an exchange details. So basically, we compute some metrics before the buy operation and after the buy operation. So for each exchange, we record and compute these particular features that will allow us to recognize this kind of perfect transaction in the future. And obviously, this operation is executed for each stock that you want to put inside your wallet. So at the end of the day, what you get is you have like, let's call it like a brain space. And in this brain space, we have a list of perfect exchange details with all these features specifically for each stock. So for each stock, you have a list of, let's say, fingerprints that you will use in order to recognize the best transaction. So yeah, that's the point here. Some notes on the exchange details we tested is that putting like a common wisdom all together is not working well, because each stock has its own behavior, its own traded amount, price, and quantity. So it's better to like consider each computed exchange details for each stock that you want to put inside your wallet. That's why we have that like siloed exchange details separated between one stock and the other. Yeah, so basically because the stocks have different behaviors in there. So now let's go directly on how we tackle the adversarial, the concept drift during the training part. So That is the basic unit that we have here. So we call it the stock online, so the data that you record, that you see when you trade online. And the basic values that we consider is the date time, the code of the stock, ledger price, ledger quantity, money, price, and quantity. During training, we use the concept of Taylor polynomial. And so basically here we say that as we are more near to the observation point in time, the values that are near the observation point are the more precise also for the points in the future. So using that concept here, what we get is that we have the stock online at time t, so the point in time that we start the observation. We want to predict which can be the future value, so the value that we can predict at time t plus 1, t plus 2, and t plus 3. And in order to do that, we use the nearest value around our observation time, so in t minus 1, t minus 2, and t minus 3. So we use the previous values in order to predict the future ones. So that's the first step. When we get that, we simply compute like data augmentation on that. So we simply record the little delta that we record for that stock online, and we create different augmented version of that stock. So we simply augment the time series and create different version of that time series in time. So in order to have some replicas that can also allows us to predict next behavior of the stock in the future, in the near time, obviously. When we have that, so different values of this time series augmented, what we perform here is to compute the best transaction for that time series. Then from the best transaction, we derive the exchange details. And yeah, that's it. So we will use this kind of exchange details to recognize the best transaction when we will go live in the future. So validation time. Here is a simple script that summarizes what we see here in the process. Maybe it's better to see here like pseudocode version. So in order to during training, what you have to do is to simply specify a time range where you want to go back in the past. So you get that kind of data. You perform like an augmentation to create like different version of the time series for that specific stock in the time. And then when you generate this different kind of time series, so augmented data, you simply compute the best transaction for each time series. You compute the exchange details, and then you put the exchange details, so the best fingerprints, in order to predict and to recognize the best transaction in the future. And here you have the brain space at this point. Some notes regarding the adversarial training is that some stocks have behavioral characteristics that are very similar in a 5-day period. So in the days that are near one to the other, the behavior is very similar, while other stocks like in the US market change rapidly. So they change the behavior in a matter of minutes. So it's very important to choose the window in order to make the correct prediction. And here, the concept of Taylor polynomial helps a lot, because as you are near the observation point in time, the more the accuracy is higher. And finally, you have to recompute the brain space. You have to perform this process every day. So when the market closes, use the last record data for that stock, and you recompute the brain space in order to equal every little derivation, every little change and concentrate during each stock in the market. Finally, the adversarial validation part, how we tackle the adversarial, the concentrate during the validation, so in real time. That's a little simple concept. So what happens is that at time t, using that observation, we build the exchange details in time t. At time t plus 1, then we update the previous exchange details. So now we compute the exchange details by considering the stock online at time t and t plus 1, and also create new exchange details using the observation on time t plus 1. And go on using this kind of steps. So at observation t plus 2, we compute the exchange details at time t plus 2. We update the previous 2. At this point, you simply have to compare each exchange details that you built with the previous one that you computed before. Obviously, in order to make this compare different exchange details, you have to choose a confidence level. And obviously here, the more the confidence level is low, the accuracy will be higher, but you have to produce many, so the data augmentation order size will be very large in order to take this kind of precision, and also the other part. So the higher will be the confidence level, and you can maybe rely on less data, but maybe the precision is not as higher in the previous case. Last thing here, when you pass from sim to real in this kind of building in real time, exchange details and observe features, in simulation, everything is going well. But when you go in real time, so when you go in production, maybe you have to tackle like network errors. So you have to stop your computing different exchange details. You have to tackle this kind of errors and then restart from the point that you posed before. And also, when you make an order in simulation, you make an order and that's it, the order is executed. In real time, when you submit an order for a trade, you have to wait that the order will be executed. So maybe it's put in a queue, maybe it is executed after some minutes or hours. So you have to take into account the different state of the order from the point that you submit the order until the point that the order is executed. And that's changed a lot, maybe the prediction. So yeah, so but that's it. Basically, these are the takeaways. So the concept drift, specifically in different fields, then concept drifting stock market, a little focus on the Italian market, and how we tackle the concept drift from the point of view of the adversarial training and validation. We use this data set here for data that we use for each stock. We are Giacomo and Federico. Thank you so much for your attention. Last simple thing here, the format of the slide is very lightweight, but basically we take inspiration from this website that I think you know very well. And the final part of the website, you find this link that tells you how a website and presentation must be like presented in order to be lightweight as possible. So we use that paradigm here. So yeah, thank you so much.